recent years, programmable logic controllers have been developed, refined, and installed in large numbers throughout the power industry and indeed throughout industry in general. In the power industry, the term PLC can prove to be confusing, as we are all accustomed to power line carrier, PLC. Thus, we will often find these controllers referred to as a microprocessor controller, a programmable controller, a computer control system. Traditionally, control has been performed by hardwired relays which open or close contacts to operate control devices in a specific sequence, depending upon the input signals. In the much smaller PLC, control is performed by the computer software opening and closing switches in response to input signals. Moreover, once a hardwired relay panel is installed and wired to perform a specific function, a great amount of effort would be required if the control process requirements were to change. We would need to sit down and redraw the circuits, perhaps purchase additional equipment, and then rewire the components. In the case of the PLC, the process logic is contained in the software. Thus, if a process change is required, it is simply a matter of rewriting the software program. In fact, a typical compact PLC can be moved from one location to another and programmed to perform a totally different task. You will find the same standard PLCs used for such widely different jobs as boiler burner management in the power station, automatic gas turbine startup, automatic switching of circuit breakers, voltage control, production line control in a factory. It is the programmable logic feature which makes this type of controller so useful. Of course, for many simple tasks, fixed logic is quite adequate. For example, in your TV set or washing machine or automobile, small microchips are installed, each containing a fixed logic in order to carry out a specific task. But what do we really mean when we refer to process logic? Well, the term logic is applied to the sequence of actions and control parameters which are needed to perform a certain function. Let's look at some examples. Here we are looking at the main oil pump, which is providing lube oil for a gas turbine. An auxiliary oil pump is installed so as to maintain lube oil flow in case of failure of the main oil pump. The auxiliary oil pump will cut in automatically when this low pressure switch detects that the oil pressure has fallen to its set point. This logic diagram shows that in order to energize the auxiliary oil pump starting relay, we need to fulfill several conditions. The pressure switch must be on due to low oil pressure. The auto manual switch must be set to auto, and all permissive circuits for the pump must be on. The AND gate shows that all three conditions must be met before the pump will start. But in this particular oil system, imagine what would happen when we shut down the gas turbine and switch off the main oil pump. The auxiliary pump will start up and run unnecessarily. So to prevent this, we need to add another AND condition, an ON switch, which is closed when the gas turbine is actually spinning. While the unit is shut down, we may wish to test the oil pumps. In this case, we need to provide a manual start for the auxiliary oil pump. So now we have to introduce another element to the logic diagram. This is the OR gate. The auxiliary oil pump can be energized by a signal from either the auto start element or the manual start element. And what conditions must be satisfied for the manual start? Well, in this case, we need the auto manual switch to be set to manual, and the permissive contact to be enabled, and the starting circuit from the manual switch to be energized. Now, if we were to draw this logic as an electric control circuit diagram, it would probably look like this. Here we have our DC bus available to energize the auxiliary oil pump starting relay. This is shown as a relay here, but in many control circuits it may be replaced by a transistor. To start the pump automatically, the following contacts must be closed. The turbine must be running with the on contact closed. The auto manual selector switch must be on auto, and the pressure switch must be closed due to low oil pressure. The contact from the permissive relays is normally closed. However, if a protective device is activated, this contact will open so that the motor cannot be energized. Now let's look at the OR circuit. This is really a parallel circuit, sometimes called a branch circuit. To start the pump, the auto manual selector must be in manual, and the start contact must be closed. This would normally be energized by a starting circuit, which would include a seal-in contact arrangement around the starting switch or push button. Once again, the auxiliary pump and motor are protected by the same permissive contact. Right now, let's move on to look at another example of logic, this time on a distribution feeder. This sectionalizer is located downstream of the recloser. The sectionalizer does not have sufficient capacity to interrupt fault currents. Instead, it is used to open and so clear a faulty circuit once the line is dead, that is, after the recloser has tripped the third time. In order to do this, the sectionalizer control circuit must count the number of times that the recloser has tripped and reclosed, and it must also register the fact that fault current is passing through the sectionalizer. We certainly do not want other sectionalizers tripping unfaulted circuits. When the sectionalizer detects a heavy flow-through current, it starts the counter. This is often referred to as resetting the counter. The counter registers the number of times that voltage falls to zero as a result of the recloser tripping. First, we have the initial trip, then the first reclose, followed by a trip, and the second reclose, followed by a trip. So that is 3 counts of zero voltage. This is one condition for energizing the sectionalizer trip. A second condition is that voltage on the line is actually zero at the time. So this is an AND requirement. The circuit diagram would probably look like this. The high current flow detector starts the counter. But remember, this circuit is going to be interrupted 3 times. So we need a seal-in circuit here in order to make sure that the counter is not interrupted. After 3 counts of 0 volts, the associated contacts close on this branch, and providing the voltage is 0 on the line, the trip relay will be energized. This is a normally closed contact that will be held open as long as voltage remains on the line. One thing we have to remember here is that as soon as the sectionalizer is opened, we need to break the seal-in circuit. This is to allow us to close the sectionalizer again after the fault has been cleared. This is achieved by including an auxiliary contact which opens when the sectionalizer opens. Let's now look at the arrangement for a recloser. Here, the recloser trips on high current and recloses after a time interval of, say, 10 seconds. The idea is to allow a temporary fault such as lightning to clear during this time delay. The recloser is allowed 3 reclosures before finally locking out in the tripped position. This control circuit shows the arrangement. When the recloser trips due to high overcurrent, this auxiliary contact closes and starts both the timer and the counter. The counter circuit is shown on the 3rd rung of this diagram. Note that once the counter contact is made, it is latched in by this seal-in contact. This is because we need it to keep counting through several reclosures and not reset each time. Now, when the timer times out, its contact closes, so energizing the reclosing relay. Note that the counter contacts are normally closed until it completes its preset count. If the fault still exists on the feeder, the recloser will trip again and repeat the sequence. On the fourth trip, that is after 3 reclosures, the counter output is energized, so opening the normally closed contact. This prevents further reclosure until the fault has been cleared and the control circuit reset. To do this, the recloser is switched to manual control and the counter seal-in contact is opened, so returning the circuit to the start condition. We have included in your workbook additional logic diagrams and a list of available functions, for example, NAND, NOR, etc., so as to allow you time for practice and study. We've seen that logic can be expressed in several forms. One is a simple written series of statements indicating the sequence of actions required and the conditions necessary to achieve the desired action. The statements would also indicate the non-permissive conditions when action must be prohibited. We can turn these statements into a logic diagram using logic gate symbols like this. Note that as well as the AND gate and the OR gate, we also show NAND and NOR gates. The NAND gate is simply a combination of the 2 words not AND. This means in this particular circuit that if all 4 inputs are energized, the output would be 0. However, the positive input of any 1, 2, or 3 will produce a positive output. Similarly, the NOR gate indicates that a positive input of either one or both signals will result in 0 output. Logic can also be presented by the electrical control diagram. This is known as ladder logic for obvious reasons. To work out the sequence of actions, we start at the top rung, left to right, and work our way down to the bottom. The top rung will usually initiate action on the second rung, and so on, all the way down. In the solid wired scheme, all of these contacts represent relays, and these are connected to various input and output devices. Input signals to the control scheme are fed from such devices as pressure switches, temperature switches, current and voltage sources, mechanical position switches such as travel limit switches, electrical on-off switches, and so on. Input signals give information as to the status of the process being controlled. Outputs from the logic circuits are usually in the form of an energized relay or transistor, which will initiate the desired action, for example, to start or stop machines, switch circuits in or out, trigger alarms, provide indication, increase or decrease speed, for example. In many cases, the logic circuit includes such devices as timers, counters, and latching devices. Now, at this point, let's take a break, and then we'll come back and see how all this is achieved in the programmable logic controller. For now, though, please switch off the tape and review this material in your workbook. A definition of a PLC could be given as follows. It is a digital electronic device that contains instructions in its programmable memory, which enables it to implement specific functions such as logic, sequence, timing, counting, arithmetic. This simple block diagram shows the principle. Inputs from pressure switches, temperature switches, and other sources are fed into one side of the controller, a black box in this instance, and outputs to solenoids, motors, relays, etc., exit from the other side. The controller has to continuously read the status of the inputs, manipulate the data according to its pre-programmed instructions, and then set the outputs accordingly. This particular model of PLC very closely resembles our block diagram. The terminal strip on the bottom allows us to connect up to 12 input points. The output points are connected to the top terminal strip. An interesting feature of this unit is that status indicating lights are provided for each terminal point. From this, we can observe which of the inputs are in the on position. Similarly, we can see which of the output signals are off. This communications port allows the PLC to communicate with other microprocessors or a central master computer which collects data. The communications port is also needed when we wish to reprogram the PLC. Perhaps we have to change certain reference values, or indeed change the process entirely. This is done by connecting the programming unit. This may be a handheld device or, more commonly, a keyboard. The programmer includes a screen and a number of keys for entering functions to cancel or modify the program which resides in the CPU memory. Like most digital equipment, the central processing unit works on low DC voltages. The required voltages are developed in the power module, which is contained in the unit. This allows us to connect the controller to a local power supply, say 125 volts DC or 115 volts AC, or perhaps a 24-volt DC battery circuit. Because of its relatively small number of inputs and outputs, this compact type of PLC is generally used for dedicated control schemes. For example, water level control, standby pump stop and start, or similar simple systems. For more complex control schemes, a rack-type PLC would be installed like this. This unit contains several different printed circuit modules which can be selected to suit the specific purpose. Typically, the modules would include several input and output cards, input and output control modules, cards for logic memory, logic control, and arithmetic control, a communications module for interconnection with other devices, a power supply. This module needs to provide power for both the PLC and its modules and must be selected with this in mind. This particular processor can handle up to a total of 512 inputs and outputs, so you can see that it has a fairly large capacity. Irrespective of the arrangement of hardware, all PLCs operate in a similar manner. This block diagram will help us understand how it works. The input signals from the sensing devices may be analog or discrete on or off signals. For example, an oil pressure switch will be on when the set point is reached and action is required. At the input interface, all of the on or off signals are converted into digital signals for storage in the input image memory. The binary digit 1 represents the on state, which is called the set condition. The off state, that is, the reset condition, is represented by 0. The arrangement of ones and zeros in the memory is a reflection of the current status of the input points. By scanning this input image memory, the CPU can enter this information into the register for processing. The CPU carries out this scan every few milliseconds and compares the indicated status with the logic which is programmed into the memory. If the result indicates that some action is required, it will change the appropriate output points on the output image memory. This output digital signal is then converted by the output interface into an on or off power signal. The CPU is said to read the input signals and write the output signal. In performing this function, the CPU is directed by the operating system, which is built into the computer and contained in the permanent memory. In addition to this, the memory stores other information such as the program logic, that is the ladder diagram program, plus all relevant data. Different types of memory are used for different purposes. Let's look at the features of RAM, ROM, and EEPROM. RAM is the term given to random access memory, which is really temporary in nature. We can write data into this memory and read data from it. RAM is normally used to store program data which needs to be modified, ladder programs which are being developed, the image memory, that is the current status of input and output points. Unless the RAM is supplied with a backup power supply, all of the data in the memory will be lost if the PLC is turned off. For this reason, permanent data and operating instructions usually reside in the read-only memory. This is known as ROM. This part of the memory is actually programmed during manufacture, and it is non-volatile. This means the data will not be lost if the PLC is switched off. A special type of ROM allows us to change programs which reside in its memory. This is known as the EEPROM, that is, erasable programmable read-only memory. The program can be erased by exposure to ultraviolet light and a new program entered. One obvious application of EEPROM is the storage of the ladder logic, as we may need to reprogram this from time to time. You will also see the term EEPROM, which refers to an electronically erasable programmable read-only memory. As the CPU continuously processes data, it is drawing information from and providing information to the different memories via the communication bus. Each of the inputs and outputs must be individually identified so that the CPU can compare this to the correct point in the logic program. Each of these points is given a specific address. In programming, they may be given simple numbers, 0, 1, 2, 3, 4, etc., along with an identification number for the controller itself. Of course, within the computer, this is translated into binary form. You will remember that we have already discussed in earlier tapes the binary code as used in digital operations. As the CPU completes each scan of input data, the information is processed through the logic, and if necessary, an output signal will be generated. This could be, for example, a simple on signal to start a motor or some other activity. But there may be other more complex actions involved in the logic. For example, a time delay may be required at some part of the process. In other applications, a counter may be involved. These functions are actually contained within the computer software. So instead of having to energize an external time relay, which would then initiate the on signal, all of this activity can be performed within the PLC. The timer obtains its signal from a built-in clock oscillator. The counter works by counting digital pulses. Another useful function which is contained in the PLC is the latching and unlatching function. This allows us to program into the logic the seal-in of certain contacts. We can also unseal, that is, unlatch the contact when conditions demand this. So-called auxiliary relays are used for these functions, but of course these are not really separate devices. The software is written so that the particular step of the process acts like a relay. The question arises, how long does the CPU take to perform all of this? Here we are talking about the throughput time, that is the CPU time plus the input-output time. Well, on a relatively simple scheme, it may take from 1 to 100 milliseconds unless, of course, a deliberate time delay is incorporated in the logic. However, large PLCs may need to control several independent control loops. So in this case, the time period between scans would be extended. The large CPU is said to be multitasking, and usually some order of priority is established in allotting the tasks. For example, it may be considered necessary for certain control loops to be scanned more often than others. This is programmed into the PLC using the time clock. Over and above this, an emergency condition, say a machine alarm, may direct the CPU to interrupt its existing task and switch to the emergency item. When looking at PLCs, we must remember that we are not talking about protection relays. Discrete protective relays are still installed to protect equipment. The PLC looks at the overall control loop and takes action to satisfy a number of different conditions. However, some protective functions are often included within the control logic. Now, at this point, it's time for us all to take a break, and then we'll come back and take a look at details of PLC inputs and outputs. For now, though, please switch off the tape and review this material in your workbook. In this segment, we're going to look at typical PLC arrangements for handling input and output signals. In most installations, hardwiring is used to connect the sensors in the field to the input terminals at the PLC. Most of the signals are of the on-off type, known as discrete signals. Devices such as pressure switches, temperature switches, and limit switches all provide an on signal when their preset conditions are met. Closing the contact completes a circuit and applies a voltage to the PLC input terminal. Here, the voltage source is obtained from the PLC itself. The advantage of this is that it allows us to determine the level of voltage which will be applied to the circuit. Quite commonly, this is 24 volts DC, but other voltage levels such as 115 volt AC or 125 volt DC are also used. All of these voltages are far too high to be fed directly into the CPU, so a certain amount of signal conditioning is required at the interface. The interface is in fact the input module, which sits between the input terminal and the image memory. This module performs several tasks, such as provision of the required voltage levels for sensing and reduction of each signal voltage level down to that required for operation of the CPU. Provides electrical isolation between the incoming signals and the CPU. This is to protect the CPU from spikes and other undesirable external effects. Converts the incoming voltage signal into computer binary language for storage in the image memory. One common method used in the interface to reduce voltage and provide the necessary isolation is to pass each incoming signal through an opto-isolator. This arrangement shows just one input terminal, and this particular sensing circuit uses 24 volts DC, which is supplied from the PLC. When the pressure switch closes at the sensor, the 24 volts is applied to the input terminal of the PLC. Current passes through several resistances as it returns to the zero voltage bus. The objective of the resistance is to reduce the voltage applied across the opto-isolator. When current passes through this LED, that is a light-emitting diode, the light triggers the phototransistor to provide a signal to the internal interface. The second LED provides indication when the signal is on. Each of the individual input terminals will need a circuit similar to this. But incoming signals are not always discrete on-off signals. In some cases, we may need to input analog signals. For example, voltage, current, speed, a position indicator, in fact, any required measurement of a continuously varying quantity. For many analog signals, the voltage source is obtained at the sensor, usually from a transducer which typically provides a 0 to 10 volt DC signal. Before the analog signal can be used in the CPU, it must be converted to a binary code digital signal. For each incoming analog signal, the input module must provide analog to digital conversion. The output from the A to D converter is in binary form, representing the input value at any specific time. Okay, so much for the input circuits. Now, let's move on to look at typical arrangements of output signals from the PLC. The function of an output signal is to energize a control device such as a contactor to start a motor, a solenoid to operate a circuit breaker, indicating and alarm circuits, and so on. The output module provides the interface between the CPU output image and the actual output terminals. Its main function, then, is to convert the CPU's digital output signal into a power signal at the associated output terminal. This diagram shows one method using an electromechanical relay. The relay coil is connected across the internal 24-volt DC supply, and it is switched by a small transistor. This, in turn, is activated by an on signal from the CPU. Note that when this signal is on, it energizes a status LED. This provides the output indication that we spoke of earlier. When the relay coil is energized, its contacts close, and this completes the external circuit, which in this case operates a solenoid to close a motor contactor switch. The operating voltage for the solenoid is provided from the contactor itself. The PLC relay merely completes the circuit. The operating voltage will probably be 115 volts AC, or perhaps 125 volts DC. This type of output arrangement provides good electrical isolation between the CPU and the external power system. However, it does have some disadvantages. It is relatively slow and therefore increases the response time of the control scheme. Electromechanical relays are subject to contact bounce, and this may provide problems for the output device. When the coil is energized, it may generate inductive currents, which could interfere with the CPU operation. Often a diode is connected across the coil to help reduce these inductive effects. The biggest problem, however, is the limited capacity of the output signal. These output relays are usually quite small, with a maximum capacity of, say, 46 VA. That means that with an applied voltage of, say, 115 volts, our output current would be limited to 400 milliamps maximum. Of course, an external relay can always be installed if heavier current is required by the control device. In order to decrease the response time, transistor switching is often used instead of the electromechanical relay. This diagram shows one arrangement. The switching transistor operates on the internal 5-volt DC supply. When the output from the image memory is on, it triggers the transistor, and this applies the 5-volt DC to the output terminal. The switching capability of a light-duty transistor is typically limited to about 25 milliamps. And therefore, if the load device requires greater capacity, a power transistor will have to be installed adjacent to the load. In some PLCs, power transistors are built internally, so each of the output terminals is capable of switching higher current flow, typically 500 milliamps at 24 volts DC. In this arrangement, the 24 volts DC is obtained from the load device. Note that the transistor is used only for switching DC circuits. Where AC switching is required, the DC output signal from the PLC is used to trigger an external or internal solid-state relay, such as an optically isolated triac. These devices usually have the capacity to switch 0.5 to 2 amps. Okay, so far we've looked at output signals from the PLC to perform on-off switching of AC and DC circuits, but in addition to these on-off signals, we may on certain circuits require the output signal to be analog, that is a variable signal, to perform such load functions as variable speed control, governor control, voltage regulation, and so on. The binary output signal from the CPU must be converted to an analog signal. This is performed by a digital to analog converter, which is located in the output module interface. This is just the opposite arrangement to that for handling incoming analog signals. Output analog signals are typically between 0 and 10 volts DC or 4 to 20 milliamps DC. We have already mentioned the need for isolating and protecting the CPU from interference due to so-called noise on the input signals and power supply. Noise is the term given to switching transients, voltage spikes, radio frequency interference, AC line hum, semiconductor noise, and so on. The effect of switching transients can be reduced by connecting a suppression circuit across relay contacts. This circuit consists of a capacitor and resistance in series. Additionally, MOVs, that is, metal oxide varistors, are connected across input devices so as to absorb voltage spikes. Filters can be connected to reject 50 or 60 hertz interference, that is, AC line hum. Shielded cables should be used throughout, and all grounding should be made at a single point only. In discussing inputs and outputs to the PLC, we have seen that there are a variety of arrangements available according to the specific application. Even though PLCs are interchangeable to a certain extent, we must certainly be aware of the types of input signals available and output signals required by the installation and specify accordingly. In some PLCs, plug-in input and output modules are used. This facility enables us to configure the interface to suit each specific terminal requirement. So, now that we've looked at basic operation of the PLC and discussed the input and output circuits, it's time to take a look at programming. But first, let's take a break. Please switch off the tape now and thoroughly review this material in your workbook. In earlier segments, we noted that the PLC's logic is retained in the programmable memory, usually EEPROM. The instructions are stored in computer language, that is, binary code. In order to modify a program, or indeed to assemble a new program, we input instructions or commands to the controller from an external programmer. The programmer is actually a small portable computer which converts our instructions into binary form and enters this directly into the EEPROM. To make it easy for us, the programmer is equipped with a screen and a series of push buttons, each containing a specific logic function. Also provided are means of addressing each input and output point. We instruct the program which specific input signal to read, what to do with the information, and subsequently how to set or reset each specific output signal. Special care must be taken when entering decimal values to place the decimal point correctly. As we've noted before, program logic instructions can be prepared in several different forms. First, we could have a series of written statements indicating the sequence of conditions required to energize each specific output contact. Another method is to prepare a logic diagram using logic gate symbols. The third and most common method is to use a ladder diagram representing electrical contacts and functions. Many PLC programmers allow us to input written instructions by pressing the appropriate buttons. This table shows a typical list of programming, that is, coding instructions, as provided by a PLC manufacturer. On the left, we have the inscription as it appears on the push button, and on the right is a description of what this actually does. Personally, I find that I need yet another column to interpret this description. For example, supposing we wanted to enter this logic into the CPU memory. The output is shown as a control relay, and this may be energized by either of the two branch circuits. Input contacts IN1, IN2, IN3, and IN4 must all be closed to energize the control relay. Or, input contact IN5 must be closed. Each of the individual input and output contacts must be given an address. In this example, they are simply numbered 0 to 4. To enter the coding instructions into the program, we simply enter the address 0 equals IN1, and then add the instruction by its particular push button. In this case, the word load means that IN1 contact must be closed. Subsequently, addresses 1, 2, and 3 are entered, each with the AND instruction, meaning that IN2, IN3, and IN4 must also be closed. Address number 4 refers to contact IN5, and as we know, this is an OR contact. So this instruction is entered into the program like this. If these conditions are met, address 5, which is the output control relay, will be energized. It is therefore given an output instruction. In this example, address number 6 is used to indicate the end of the sequence. Obviously, there are other systems where other conventions are used. Let's look at another example. In this case, a multiple OR operation. The logic diagram shows that the control relay will be energized when any one of the input contacts, IN1, IN2, IN3, or IN4, are closed, providing that contact IN5 is also closed. The instructions entered into the program for each address would look like this. Input contact IN1 must be loaded, that is, closed, or contacts IN2 or IN3 or IN4 and contact IN5 in order for an output signal to energize the control relay. Nowadays, many PLC programmers allow us to build up a logic diagram from the keyboard instead of using symbols for written instructions. In this method, we simply select the appropriate address and then add contacts and other functions as we move across each rung of the ladder. Branch circuits can be drawn in and additional rungs added as required. Note that it is necessary to include an end rung at the completion of each sequence. Different coding methods are used by the different PLC manufacturers, although they may appear to be quite similar. Make sure that you practice and learn the program coding details for your own particular PLCs. Let's look at a few more examples of program logic. Many logic diagrams become quite complex, and in this case, the written ladder code is simplified by using sub-circuits or blocks. For example, here we have two OR sub-circuits which are in series to energize the control relay output. To simplify the ladder code, this is broken down into the two sub-circuit blocks. Address 4 on this ladder does not refer to any particular input or output point, but to an examination which must be performed in the register. To satisfy this condition, both of the sub-circuits, that is the blocks, must be on. This in turn will provide an output to energize the control relay. Note also that an additional address number 6 is added to indicate end of sequence. Further examples of multiple block operation are included in your workbook to allow you more time to study these in detail. Here is the logic arrangement for a NAND circuit using normally closed input contacts IN1 and IN2. When there is no input to points IN1 and IN2, the output control relay is energized. With an input signal on either point, Its contact will open, but the control relay will continue to be energized via the other contact. However, with an input signal on both points, IN1 and IN2, both contacts will be opened and the output will be de-energized. The ladder coding instructions are shown here. The NOR gate logic is similar, except that the two input contacts are in series. In this case, if either input 1 or 2 receives an input signal, its contacts will open and consequently de-energize the output relay. This logic circuit shows the arrangement for latching and unlatching, that is, resetting. In this arrangement, the IN1 contact is closed temporarily by holding a push button. This, in turn, energizes the control relay CR1, which closes the seal-in contact. When the push button is released, IN1 contact opens, but the circuit remains latched in. In order to reset, that is, unlatch the circuit, input contacts IN2 and IN3 must both be closed to energize auxiliary relay AR1. This, in turn, opens the auxiliary relay contacts and unlatches the primary circuit. Of course, this auxiliary relay is not a relay in the true sense of the word. It is merely a function which is part of the software program. In many programmers, this enables us to include latching and unlatching arrangements by simply entering the appropriate function. This logic circuit shows us how the latch could be reset using a counter. When the push button IN1 is pressed, it resets the counter as well as energizing the control relay CR1. Each time that contact IN2 is closed, it is registered by the counter. After 3 operations, the counter output is energized, and this in turn opens contacts CR1, so breaking the seal and unlatching the primary circuit. This example shows the inclusion of a timer. When the push-button contact IN1 is closed momentarily, it is sealed in by the auxiliary relay. The timer is started, and after 5 seconds, the timing relay contacts close, energizing the control relay output. However, if the IN2 relay becomes energized during the delay period, its contacts will open. This breaks the seal-in circuit and de-energizes the timer, thus resetting it to 0. The IN2 contact is probably a permissive for the particular control device. In effect, during startup, this circuit is allowing the permissive 5 seconds to check conditions before allowing the start to proceed. Another very useful function, the jump function, allows us to skip over defined parts of the logic under certain specified conditions. This changes the response time of the controller, so be sure this is what you want to do. Okay, so I think we have seen enough of ladder logic diagrams. We've added a few more examples in your workbook so that you can have fun working through the sequence to see what they do. It is even more important that you get hold of the ladder logic for your own PLCs and study these until you acquire a thorough understanding of the functions of each rung. Many programmers are helpful in allowing you to access the control circuits online. You can examine on the programmer's screen each rung of the ladder and observe which contacts are open or closed and the state of inputs and outputs. You can also force close or open selected input and output contacts in order to check the operation. Usually, forced operation of input contacts causes the outputs to be isolated so as to prevent inadvertent operation. Forced outputs can bypass safety permissive contacts, causing machine action. Therefore, use care when forcing outputs. This facility is a tremendous help when troubleshooting, not only for problems within the PLC itself, but also within the external input and output circuits. Clearly, getting accustomed to using the programmer is really the essence of setting up and maintaining PLC installations. Get as much practice as you can. So to give you an opportunity for this, let's take a break right now. and then we'll come back and see how the PLCs have grown. For now, please switch off the tape and thoroughly review this material in your workbook. It was inevitable that, like everything else, the PLC had to grow. The original concept of the PLC seems to have been based on the need for rugged, compact units that could be used in industry for controlling production line items and machine tools. In general, each individual controller was mounted close to the machine and handled a distinctly limited number of tasks. Although this arrangement is still widely used in many factories, PLCs have nowadays expanded to become complete distributed control systems. In one arrangement, up to 8 PLCs can be connected together via a common communications system. The advantage of this is that any one of the PLCs can be accessed from a single unit. For example, the programmer can be plugged into, say, PLC number 8, and then used to troubleshoot or program this PLC, or monitor any one of the other 7 PLCs. Another advantage is the facility for extracting data from all 8 PLCs and feeding this into a central computer. At the central location, we can learn what each PLC is doing at its individual location. In this type of arrangement, the total distance involved is usually limited to an area of about 4,000 feet in circumference, unless special arrangements are made to boost communications signal strength. In order to clearly identify data from each of these PLCs, it is necessary to assign a number to each individual controller. Typically, then, a specific input address may read, say, 4IN2. This would mean that the addressed data point is on number 4 controller, and it is input point number IN2. This particular system, which loops 8 PLCs, provides a total of 256 input and output points. That is 32 points per controller. However, there are a number of systems available which provide much greater capacity than that. For example, in this system, 10 I/O racks may be connected to the master controller, and each of these racks can control up to 10 input or output modules. So with each module containing 8 inputs or outputs, we can have a total of 800 inputs and outputs, in addition to the 40 or so contained in the master controller. Each of the I/O racks contains its own power supply, plus a receiver for communications with the master controller. All of the 10 racks can be connected on the same loop, providing that the maximum cable length is not greater than 50 feet. This arrangement is known as a local I/O station. If a greater distance is required, then it is necessary to add a transmitter in order to boost the signal to the next rack. This may be up to 500 feet in distance and is known as a remote I/O station. An additional 3 stations may be added in this manner, so giving a maximum distance of 2,000 feet. If a longer distance yet is required between the master controller and the remote station, then a serial communication link must be installed between them. This may consist of a twisted pair cable, which would allow a distance of up to, say, 10,000 feet. For greater distance than this, an RS-232 modem link would be required. To power this, a remote I/O driver circuit board would need to be plugged in to the master controller at the sending end. So now, with this arrangement, we have a large number of input modules spread over a wide geographic area, all collecting data and transmitting this to the master controller when addressed. In the same locations, we have output modules, which are providing output signals to control devices when instructed by the master controller. I am sure that by now you are beginning to recognize the functional elements of a SCADA system. However, ideally in a SCADA system, we would like the remote terminal units to be capable of performing a certain amount of data processing and signal conditioning locally. One such system that has evolved uses so-called local input-output blocks. The input-output block is usually configured for 8 input or output circuits, and this is connected to a communications controller module, which is plugged into the I/O rack. The communications module can handle up to 30 I/O blocks. So a little bit of arithmetic shows us that with, say, 10 communications modules in a rack, we can connect up to 300 times 8 equals 2,400 input or output circuits. And that's just for one I/O rack. But just as important as this extended capacity is the fact that the block itself contains a certain amount of processing capability. The I/O block is actually made up of 2 parts, the terminal assembly and the electronic assembly. First, the terminal assembly is where the field wiring is connected. For example, power supply to the block, input signals to the block, and output signals from the block. Located within the terminal assembly is the EEPROM, that is the electronically erasable programmable read-only memory. The program in this memory can be changed by commands from either the CPU or by a handheld monitor, which we'll look at in a moment. As you will remember, the EEPROM retains its memory even during loss of power. The electronic assembly is also contained in the I/O block. This contains the power supply, the communications chip, the microprocessor, and other electronic components. In operation, the microprocessor reads the EEPROM and the input and output status. It also communicates information to and from the CPU when addressed. The I/O block performs the useful function of converting input signals, whether they be discrete or analog signals, into digital form for efficient and rapid communication. Similarly, the output signals are converted from digital signals to power signals, which may be discrete or analog. A handheld monitor is provided to enable us to monitor the system and also to modify some of the parameters if required. This device can be plugged into the receptacle bus at the top of each I/O block. It may also be plugged into the bus controller located in the I/O rack. In some installations, the monitor is connected permanently into the bus controller so as to provide continuous monitoring. This handheld monitor is battery powered, so make sure that you keep it charged. When each input-output block is installed, the handheld monitor is used to configure the terminal arrangement. That is, to make each circuit suitable for the type of input, say analog or discrete signals, either AC or DC. Similarly, the output circuits must also be configured to meet the requirements of the output control devices. Alarm levels and other control parameters can be set using the monitor. A very important feature is its diagnostic capability. Each of the control loops can be checked out, including the hardware. This allows us to check control circuits even before they are commissioned and placed in service. Clearly, as we get more and more into this subject, we can see that we've come a long way from the simple PLC that we started with. As we all know, the development of control systems has advanced very rapidly in recent years and will probably continue to do so. If you work in this area, you will need to continuously update your knowledge, not only in the theory of the equipment, but also in the mechanics of adjustment, setup, and troubleshooting. In this video, we've tried to take an overall look at PLCs, their function and operation, and at least point you in the right direction to studying your own installations. Make sure that you read, learn, and digest all of the information contained in the manufacturer's instruction manuals. And when in doubt, which is inevitable in some cases, make sure to discuss the problem with your supervisor. Please switch off the tape now and review this material in your workbook.